Welcome to the deep dive. Today, we're jumping into something really interesting in AI. You sent over this paper, and it kind of flips things on their head, doesn't it?
It really does, yeah.
Suggesting that all this complex thinking we see, well, maybe it's not always needed. Like, can these models solve hard problems without really thinking?
That's pretty much the core question, yeah. You flagged a really fascinating piece of research. The title says it all. Reasoning models can be effective without thinking. It definitely makes you pause and rethink what's actually going on under the hood.
Right.
So our mission today, I guess, is to unpack these pretty surprising findings and figure out what they might mean.
Exactly. So the main source is this paper, just out, April 2025, on R-Clef. Comes from researchers at UC Berkeley and the Allen Institute for AI. And they've basically been testing these, top-tier models, seeing if that whole elaborate thinking process is really essential for complex reasoning. We've also got an example, right, from that AM 2024 math competition to see how the AI tackled it differently.
Yeah, a concrete example helps illustrate the difference. And the paper really tackles this fundamental idea. Do LLMs need these long internal chats to perform well on hard tasks? It feels intuitive, right? Complex problem, complex thought, but this research throws a bit of a wrench into that.
Okay, so let's unpack that thinking bit first. Traditionally, when these models reason, what does that actually look like?
Well, usually it involves generating what people call chains of thought.
Okay.
So the model doesn't just give you the answer, it builds up this sequence of steps, almost like it's showing its work.
Yeah.
Very detailed.
Right. I've seen that. They're really long sometimes, like an essay almost, the AI talking itself through the problem.
Exactly. And that can involve reflection, maybe backtracking if it hits a dead end logically, even some self-validation, checking its own reasoning before giving the final solution.
And the assumption has always been that this detailed inner monologue is kind of crucial for getting the right answer, even if it uses more resources and takes longer.
Precisely. That led to this whole idea of inference time compute scaling. Basically, give the model more thinking time, more compute power during reasoning.
Oh, resource.
By letting it generate these longer chains of thought, and you should get better results. More thinking equals better answers. Or, well, so we thought.
But then this paper comes along with no thinking. How does that work? It sounds, well, opposite.
It's strikingly simple, almost too simple maybe. Instead of prompting the model to do that step-by-step detailed thinking, they basically nudge it to skip that. They pre-fill the start of the assistant's answer with a really short kind of fake thinking block.
Fake? Like what?
Something super basic, like, okay, I think I finished thinking, and then they just let the model jump straight to the solution.
Wait, hang on. They just tell it the thinking's done? That sounds way too easy to actually work.
And that's why the findings are so interesting, so unexpected. What they found was when they controlled for the total number of tokens, the processing budget.
Right, kept it fair.
This no-thinking approach often outperformed the traditional thinking across a whole bunch of really difficult reasoning tasks.
You're kidding. So all that detailed thinking, maybe it's not as vital as we assumed.
That's the core finding, yeah. They tested this really thoroughly across 7 different demanding data sets.
Like what kind of tasks?
Oh, everything. Complex math problems like those AM competitions you mentioned, formal theorem proving, even complex coding challenges.
Yeah.
Really pushing the models.
And what were the results like? Can you give a specific example? This sounds almost like too good to be true.
Well, okay, on one data set they call it ACM 23, probably one of the math or coding ones they listed. With a really tight budget, only 700 tokens allowed, NoThinking hit a 51.3% success rate.
Okay, and thinking?
Thinking only got 28.9%.
Wow, that's almost double the success rate just by skipping the explicit thinking when resources are low.
Exactly. It really shows the power of NoThinking when you're, operating on a budget.
Okay, the paper also mentions this pass at K metric. What's that about? How does NoThinking do there?
Right, pass at K. It's basically a measure of reliability. It tells you the probability of getting at least one correct answer if you try K times.
So, if you ask it the same question 10 times, what are the odds at least one answer is right?
Pretty much, yeah. Say you use K16. Pass at 16 is the chance that at least one of those 16 answers is correct. And what's interesting is that NoThinking's performance often improves more significantly as you increase K compared to thinking.
So even if it's slightly behind on the first try, if you generate more samples, it catches up or pulls ahead.
Often, yes. It seems to benefit more from multiple attempts. Even if thinking is better at pass at 1, NoThinking can catch up or surpass it at pass at K.
So by making lots of quick, independent attempts without the long thinking, you're statistically more likely to hit the right answer somewhere in that batch.
That seems to be the idea. And, that brings us straight to efficiency. How do they compare on cost? Resource use.
Yeah, because all those extra thought tokens must add up, right? Time and tokens are money.
Absolutely. And the research showed NoThinking often uses way fewer tokens, like 2 to 5 times less than thinking.
2 to 5 times fewer, while getting similar or better results.
That's what they found. They did this analysis, a Pareto frontier analysis. It's basically finding the best bang for your buck, performance versus cost.
The sweet spot.
Exactly. And NoThinking consistently came out on top, offering a better accuracy for tokens trade-off.
That's huge for real-world use where cost and speed matter. Okay, so if NoThinking is this good, what happens if you scale it? You mentioned parallel scaling.
Yes, this is another really interesting part. Parallel scaling is about generating multiple outputs at the same time, independently.
Instead of one long sequential thought process.
Right. Imagine firing off, say, 10 NoThinking attempts on the same problem simultaneously. Each one gives you a potential answer fast.
Okay, but then you've got 10 answers. How do you pick the right one or the best one?
Good question. That's where aggregation or best of n methods come in. How do you combine or select from those n answers?
Makes sense. What strategies did they look at?
Well, it depends a bit on the task. For things like theorem proving, where you can actually check if a proof is correct.
Right, like a definite right or wrong.
You can use a task-specific verifier, basically an automated checker. You just run all the answers through the verifier and pick one that passes.
Simple enough if you have a verifier. What about other problems?
For more general stuff,
Yeah.
where you don't have that perfect check, they tried things like confidence scoring. Maybe the model indicates how sure it is.
Okay.
Or just majority voting. If several attempts arrive at the same answer, maybe that's the one.
And how did this parallel NoThinking stack up against the old sequential thinking method overall?
The results were pretty impressive. They found parallel thinkeries. NoThinking could often get better accuracy and much lower latency.
Better and faster.
Yeah, faster response times compared to the traditional thinking approach. In some cases, it beat thinking even when thinking had similar latency. And it was comparable to thinking even when thinking was allowed to run for, up to 9 times longer.
9 times faster with similar or maybe even better accuracy. That feels like it could really change things.
It's a big deal for efficiency.
You have a specific example from the experiments that shows this?
Absolutely. On the Olympiad bench math problems, this parallel NoThinking approach actually got higher accuracy than the standard thinking method,
Higher accurate.
while having 9 times lower latency, so faster and better in that case.
That's just wow, it really goes against intuition, doesn't it? You'd think more deliberation, more thinking would mean better answers.
You would think so.
Yeah.
This suggests maybe generating more diverse attempts quickly is sometimes a better strategy.
That AB 2024 math example you mentioned earlier probably shows this clearly.
It does. The paper shows the thinking response for a tough problem, and it's really verbose.
Yeah.
Tries different paths, hits dead ends, corrects itself, uses a lot of tokens.
Okay.
Then you see the NoThinking response for the exact same problem. It has that little fake, okay, I think I'm done thinking line.
Right.
And then it just lays out the solution steps and the final answer, direct, clear. Uses far, far fewer tokens and gets the right answer. No long internal monologue needed, apparently.
So it's like the model knows how to solve it already, maybe from training, and the long thinking process is sometimes just extra fluff. Unnecessary.
That seems to be a key takeaway, yeah.
Uh-huh.
But the researchers are careful to point out it's not quite that simple. There are nuances.
Okay.
The performance boost from NoThinking wasn't uniform across all the different tests. It varied a bit, suggesting the specific task matters.
How so? Where did it maybe not work quite as well?
Well, on MiniVef and ProofNet, those are the theorem-proving datasets.
Right, the logic-heavy ones.
NoThinking was about comparable to thinking if you only looked at the first attempt, pass at 1.
Okay, so similar on the first try.
But it achieved that using way fewer tokens. So even for tasks that seem to demand careful steps, maybe the explicit thinking isn't crucial just to get one correct answer, especially if you care about efficiency.
Interesting. The paper also mentioned something about answer diversity. How varied were the answers from each method?
Yeah, they looked at that using entropy, basically measuring the variety of the answers. They didn't find one method was consistently more diverse overall.
Okay.
But NoThinking tended to show more consistent diversity across different questions within the same task.
More consistent diversity. What does that mean?
It means, like, for most questions, NoThinking produced a similar spread of different answers. Thinking might have been very diverse on some questions, but very narrow on others. And the researchers suggest this more consistent diversity from NoThinking might be why its pass at K-score improved more as K, the number of samples, went up.
Ah, okay. So because it's maybe exploring a decent range of possibilities more consistently, it benefits more when you give it multiple tries.
That's a plausible way to think about it, yeah.
Hmm.
Maybe the thinking process sometimes gets stuck down one path, too focused.
Right.
While NoThinking is a bit freer to explore, increasing the chance one of its attempts hits the mark when you take multiple samples.
This research really makes you step back and reconsider how these models work. What are the big implications here for, the future of AI?
Well, I think one of the biggest is the potential for much more efficient AI.
Yes.
Seriously, NoThinking shows a way to get strong reasoning performance even when you don't have massive compute budgets or need super fast answers.
Which could be huge for getting AI into more places, right? Real-time apps, devices with less power.
Exactly. It could really open things up.
And for you, listening in, what's the main thing to take away? Why should this thinking versus no thinking stuff matter to you?
I think it gives you a really cool glimpse inside these AI systems that often feel like black boxes. It makes you question what intelligence or problem solving even means for a machine. It suggests that getting the right answer efficiently might not always mean copying how humans think. Maybe these models learned clever shortcuts during training that we just don't fully understand yet.
Yeah, it makes you wonder, is the complex thinking just like a side effect of training? And the models have actually found quicker paths to the answer.
That's a really sharp observation. It's very possible the training embedded this implicit knowledge, these shortcuts, making the explicit step-by-step thinking often redundant at inference time.
Okay, so let's recap the key points from this deep dive. What should we definitely remember?
I'd say the main things are, 1, these advanced models can actually solve complex problems effectively without that long, explicit thinking process. 2, this no-thinking approach often gives better results for the amount of compute or time you spend, especially when resources are limited. And 3, combining no-thinking with parallel processing, generating multiple answers at once, seems really promising for both speed and accuracy.
Got it. And what's a final thought you want to leave with you, the listener? Something to chew on.
Okay, how about this? If no-thinking works because the models learned shortcuts during training, what does that mean for how we evaluate AI? Are those long chains of thought, the outward signs of reasoning, really the best measure of capability? Or should we focus more on just, does it get the right answer efficiently, regardless of how it looks like it got there internally? What does that imply for designing the next generation of AI?
That is definitely something to think about. It shifts the focus, doesn't it, from the process to the outcome. Really fascinating stuff. If you want to explore this more, definitely check out the paper, Reasoning Models Can Be Effective Without Thinking, on our compy. It's a great read about inference time, chain of thought, and the search for smarter, faster AI. Thanks for joining us for this deep dive.